In the following section, we're going to look at furnaces. The reference that can be used for this is Process Technology Equipment and Systems. It's the 4th edition, Cengage Learning, Chapter 10. So that can be used to actually add on to the next slides. So what is an industrial furnace? Industrial furnace is equipment that is used to provide heat for a process or can serve as a reactor which provides heat to a reaction. Further, there is some different furnace designs. So it varies to its function, the heating duty, the type of fuel, and the method of introducing the combustion air. If we look at typical furnace applications, industrial furnaces are used in metallurgical production for smelting at high temperatures, in heat treatment, tempering, in some areas such as food industry for drying and for fermentation at low temperatures. The metal industry has a significant share in the total industrial use and the energy consumption, of course. So if we look at some of these furnaces and what are the temperature zones they are used in, for enamel cooking, 600 degrees Celsius to 1100 degrees Celsius, heat treatment of metals, 1100 degrees Celsius, the rolling, extrusion, cooking of ceramic materials, heat treatment and pressing, usually in the order of 1350 degrees Celsius, and the melting and smelting of metals is then in the region of 1700 degrees Celsius. If you look at the theory of operation, fuel flows into a burner and is burned with air provided from an air blower. There can be more than one burner in a particular furnace, which can be arranged in cells which heat a particular set of tubes. The burners can also be on floor mounted, wall mounted, or roof mounted, depending on the design, as we will see later. And the flames heat up the tubes, which in turn heat the fluid inside in the first part of the furnace, known as the radiant section or the firebox. So this is important. So if we talk about the radiant section or the firebox, you should know that that is the same thing. In this chamber where the combustion takes place, the heat is transferred mainly by radiation to tubes around the fire in the chamber. So this tube then basically contains many tubes that contains the load that needs to be heated. So if we look at the tubes itself, so the fluid to be heated passes through the tubes and is thus heated to a desired temperature. So again, this is the load that needs to be heated. The gases from the combustion are known as flue gas. As the flue gas leaves the firebox, most furnace designs include a convection section where more heat is recovered before venting to the atmosphere through the flue gas stack. Before we go to a more detailed figure a little bit later on, let's just quickly see what are the main components, the basic components or the equipment that's associated with the furnace. The first thing I would say is a burner, of course. So we need to generate this heat. Then there's tubes. In these tubes is the load. So in other words, this is what's need to be heated. And then we also got a stack. Okay, so the stack is also important. And this is where we will get our flue gases that will exit then the system. That is after the burning took place with the specific gas. It could be methane and propane, as we will see a bit later. And then, of course, the oxygen that's also needed with that. If we look at further representation of this basic furnace components, it's more or less the same as on the previous slide, maybe a little bit more detail. But you can see again the main components is consisting of a stack. Over here it has the convection section, and there's also a radiant section. So this is the heating chambers. So the radiant section is where your higher temperature will be, and the convection section is then at a lower temperature, but it is the pipes is basically fed again. That's containing the load to the top section so that there can be more heat absorbed by the load. So it makes the system more effective. So you do have these two heating sections that was not displayed on the previous figure. And then, of course, again, you can see as in the previous figure, there was the burner. Now, again, the burner consists of your oxygen and then the fuels. I think something that's very important here is that furnaces should be operated with a minimal fuel and maintenance, of course, whereas the design of the furnace should allow for maximum heat transfer to the material in a defined time. So that's the efficiency. So the efficiency is very important of this furnace. So to ensure these conditions, these criteria should be considered. How much heat will be transferred to the material and the heat necessary to heat the mass and the loss. Just something to consider quickly. So in other words, if you look at it again, three components in actual fact is very important here. You need to have a fuel, oxygen, and a heating source or ignition source to sustain this heat transfer inside the furnace. So these three components should always be there. So that needs to be controlled very carefully, the fuel and the oxygen. Otherwise, we can have wastage on both ends, and because oxygen can cool down the furnace, if there's too much oxygen, and fuel can be wasted again if there's not enough oxygen, and it can also be dangerous then eventually. One thing that you can see in this specific diagram is that you will also have your heat. As the heat is generated, it will keep it basically self-sustained then to keep the burning process up and running, because you will have that ignition source available. So that's after you start the furnace. And then, of course, you will always have your flue gases, the exhaust that you will also get from that burning process with the fuel and the oxygen, as we will see. Okay, there's different types of furnace fuels by which heat energy is generated. It can be gas-fired furnace, oil-fired furnace, waste oil fired furnace, dual fuel, meaning that it could be a combination of gas or oil. That's a possibility, coal or electric. So if we look at in more detail at fuels itself, many furnaces use natural gases, and also, say for instance, methane is commonly a combustible fuel that could be used in a furnace. So if we need to look at the chemical reaction itself, there's a chemical equation. From this equation, I think it's just important to see what components is eventually produced after the burning process. So you can see you have your methane, and that's added to oxygen, as mentioned previously. So the two components that you will then get from this after the burning process took place is then, of course, your carbon dioxide and water. So this can be the same thing with, say for instance, another type of fuel. The equation is going to look a little bit different, of course. But so if we look at some other hydrocarbon products, say for instance, where you will have propane. So again, the propane will burn with a certain amount of oxygen, and then this will again produce then carbon dioxide with water. So basically the same as for methane, and then that could also be seen with other hydrocarbon products. Okay, now moving in detail to the different furnace equipment. On this figure, you can see that you have a stack. This we also saw on the basic figure. There's also a damper that's on the stack, an arch just to basically make sure that your flue gases are directed in the right direction, and also it will start to actually form in different pressures so that you have a proper flow of the flue gases through the stack. Um, you also have your convection tubes, a shock bank. A shock bank is just the first convection tubes that will still take a lot of heat, because your main heat is then where you have your radiant tubes, and this is inside a firebox. Okay, so that will be the largest heat exchange that will take place is inside the firebox, because that is at the closest to the burners, of course. And then your burners, again, important that you have your oxygen component as well, and insulation is also very important so that we don't have unnecessary heat losses on the furnace. Okay, so let's look at the different components. then in detail. So we're going to look at the stack and the damper. This is a very important component. So if we look at the flue gas stack, it's a cylindrical structure at the top of the heater transfer chambers, and then the breaching directly below it collects the flue gas and brings it up high into the atmosphere where it will not endanger any personnel. And then also another important component is the stack damper that's contained within the works, and it's usually like a butterfly valve, and it regulates the draft. And this is needed in the furnace eventually, which is what pulls the flue gas through the convection section. And the stack damper also regulates the heat lost through the stack. Okay, the next section is the convection tubes and the shock bank that is just below the stack, as you can see there on the picture, is indicated in red. So the convection section is located above the radiant section, where it is a cooler to recover additional heat. So again, as I mentioned, that's to make the whole process more effective. So the heat transfer takes place by convection here, and the tubes are finned to increase the heat transfer. The first three tube rows in the bottom of the convection section and at the top of the radiant section area is usually bare tubes without fins and are known as the shield section or the shock tubes. So named because they are still exposed to plenty of radiation from the firebox, and they also act to shield the convection section tubes, which are normally less resistant material from the high temperatures inside the firebox, of course. Okay, now moving to, I would say, the main section of the furnace itself. That's the radiant tubes and also the firebox. So the radiant section or the firebox is where the tubes receive almost all its heat by radiation from the flame. In a vertical cylindrical furnace, the tubes are vertical. Tubes can be vertical or horizontal, placed along the refractory wall, in the middle, and so forth, or arranged in cells. Studs are used to hold the insulation together and the wall of the furnace. So usually it's in a series of tubes, horizontal, vertical, hairpin type connected at the ends with 180-degree bend, or helical in construction. And the radiant coil absorbs heat through radiation. They can be single pass or multi-pass depending upon the process side pressure drop allowed. Radiant coils and bends are housed in a radiant box. So again, what we're trying to do here then is we need to maximize the area. So by maximizing the area, we have the most efficient heat transfer. Okay, and so we're moving to the last equipment associated with the furnace. I would say the most important equipment, and this is then of course the burners. So if we look at the burners, looking at the picture above, usually it's located on the floor and the fires are fired upward. Some of the furnaces have side-fired burners, depending on the design. And then also another important aspect is the burner tiles is made of high temperature refractory and is where the flame is contained. Then also on the air part, that in actual fact complements the burners with the fuel. This is the primary air register supplies primary air, which is the first to be introduced in the burner. Then there's also a secondary air usually added to supplement the primary air, and burners may include a pre-mixer to mix the air and fuel for better combustion before introducing into the burner itself. So moving on to the furnace types. Um, Here you can see two types of furnaces. Now, the first one there, figure 10.6, is a natural draft furnace. Why is it natural draft? You can see that there's no fan that's connected to this furnace. So in other words, the air flows then just naturally through this furnace itself and then heat up the different tubes that's inside the furnace. Then you also get a forced draft furnace. Now usually if a fan is placed at the bottom or at the starting point of, say for instance, that furnace, you will call it a forced draft fan. So it forces the air through the furnace. So with this, there is a fan then connected at the bottom, and then this is just to enhance then the flow of the air through that specific furnace. So it's again important. We'll see on the next slide, you also get induced draft fan. As said on the previous slide, so on figure 10.8, we can see induced draft furnace. Here you can see that the fan is placed at the stack. So that means it's basically then again causing from a higher pressure to a lower pressure, and this causes actually the flow then through this furnace, so that you have a proper I could say heat exchange of this heated air that flows across the tubes. And then the last one that we can see is a balanced draft furnace. Now this balanced draft furnace has two fans, so it has a forced draft fan and an induced draft fan. Now it's very important that the control usually here should be linked, because otherwise if we're going to have no connection between the two fans, where you have the forced draft fan and the induced draft fan, it might mean that you will actually won't have a constant flow of air through this furnace, and you won't have a proper heat exchange. Also, for example, if the forced draft fan that's at the bottom is maybe, say for instance, letting in more air that is actually removed from the induced draft fan, this can cause a buildup of pressure inside the furnace itself, and that could also be dangerous. Okay, so if we look at figure 10.12, it's a cylindrical furnace design. So there's four designs that's represented here. You get cabin furnaces. What I think is important here is that you can just see that you have burners that's at the bottom of the floor, and it can also be maybe on the side of the furnace itself. Then one other thing that you need to see is the radiant coils, and then you also have your convection section. So again, the radiant coils is going to get the highest temperature inside the furnace, and then the convection tubes, of course, will be at a lower temperature, but again maximizing all the temperature that's available inside the furnace, so we're feeding it back again. Then we also have a cylindrical all radiant, so it's just cylindrical tubes, and then the one on the furthest right hand side is a cylindrical furnace with convection and helical coil, so it's just a helical coil, but you can see again then on the convection side on the top there's again pipes that's actually fed back, so you'll have a better efficiency of the load eventually that goes through this furnace. So the heat transfer that takes place in that is of greater value. Okay, and so we get to the last slide of furnace types. So you can see here's a representation of 6 furnaces. The first 3 on the top is just cabin furnaces with different arrangements, of course, of the convection and radiant sections. And then at the bottom you can see there's also box furnace designs and also cylindrical furnace design that was seen on the previous slide in more detail. Okay, moving on to furnace control. So let's look at the following diagram. It represents a typical furnace. What we can see here is on the red circle, that's the load that actually goes, or the charge that actually goes into the furnace. So here maybe the convection tubes is not indicated, but the radiant tubes are there. And that's inside the firebox. You can see there's pass 1, pass 2, pass 3, pass 4. So that represents then the different tubes that can go through the furnace. And then on this is just basically the pressure that's measured on each line, and also of course what's important there on the exit of that load through the furnace, you can see that there's temperature measurements there, because that's eventually what we want to achieve. We want to actually raise the temperature of the load, okay, by using the furnace equipment, and then eventually have the proper heat transfers from that heating air that actually flows through these tubes, and then eventually we need to then measure then the temperature, of course, at the coil outlet temperature. You can see that TC there. Okay, if we move from the load itself, you can see that the draft pressure is also important, so that you know how much air is actually inside and the flow of the air through this. or across the tubes, that will also constitute towards the temperature of the load. Okay, so if you go to the fuel gas, you can see that the pressure is controlled of this gas sections. What's important here, there's two parts, a pilot gas and a fuel gas. So the pilot gas will usually be on, so that will be at a low pressure, and then the fuel gas will be the gas that supplies the main heat to the furnace itself. Pilot gas will usually be on first, and then you can ignite and you can actually have the rest of the gas flowing, and this can be then controlled by a valve. Another very important aspect that's also associated with the fuel, of course, is your airflow. And then you can see that the flow of that specific air is measured then by a sensor, and that can be adjusted. There's no feedback loop indicated here, but you can think then eventually you will control the blower that actually blows that amount of air that contains the oxygen that's needed for this combustion. Some last important aspect I think that's important here is that there's also oxygen content measurement, so it's an analytical analyzer, and then also for the carbon content. So you can in actual fact measure that, and this is important so that we can see eventually, if you can recall from that equations, how much oxygen is in actual fact still, say for instance, in the flue gases, and also how much carbon is still in that flue gases. That will indicate to you if proper burning is actually achieved. So for that we can use then analytical analyzers. Okay, on again, if we look at another furnace control, more or less the same as the previous. You always have your load that is actually coming into the furnace. You'll have your stack section, you'll have your burner section, and then your air and your fuel, of course. But if we look there, the red circle again, or red colored circle, with the stack damper can actually be controlled via a controller. And this again is important for the amount of flow of air that actually goes through this furnace, and that will again have an effect on how much heat is in actual fact exchanged. Moving from the stack control itself, you can see that you have your coil inlet temperature, so we need to measure that. Usually this is quite nice when we move to control strategies, especially if you want to see feed forward and feedback. So if you have a very large system, then it's always advisable to measure also what your coil inlet temperature and the coil outlet temperature, and sometimes also to measure maybe what's the flow, so then we know how much is actually flowing through the system itself. Okay, looking at the fuel and the air supply on the burners, again you can see that here's nicely indicated that you have on the controller itself. For the fuel you have a flow meter, and you have the burner pressure itself, so you can monitor what is the pressure of the fuel that is supplied to the burners. And then also further, if you look at the air, there's a fan again and the flow meter. So there's nicely indicated you are in actual fact measuring what is the flow. So then you can nicely balance the amount of fuel that's available to the amount of air. And again, as on the last slide of the previous control structure, you could see that there was analyzers. So over here there's a tunable diode laser spectrometer. So in other words, it can analyze what is the content of the oxygen and so forth, and also the carbon dioxides and all of that inside the flue gases. And that will again determine if there was proper fuel combustion that took place, if there's enough air and a fuel ratio at the burners itself. So yeah, so again, usually on furnaces you will use these type of analyzers to determine if there was an actual fact proper burning process or combustion that took place inside the furnace. And then only the last section to focus on, I would say, is just to see that all these control signals or sensor signals actually goes towards a controller. And then furthermore, it goes to different actuators. So if we just quickly look at the green lines on the actuators, you can see that it is connected to some valves and also some dampers. Okay, almost coming to the end of the session. Um, so we basically looked at the theory behind furnaces, also where can it be used, some properties around fuel of a furnace. Then also we looked at some types of furnaces that you can find, then the main components associated with the furnace, the description of these components, and then also some control methods associated with furnaces. So the last point I just want to look at is the parameters affecting the remaining tube life. So remember that these tubes are exposed, so there's the load inside it, or the charge that actually goes into the furnace that needs to be heated. Now, so many variables directly and indirectly affect remaining tube life and are linked to the severity of operation conditions and fluctuations within these tubes. So although the main parameters are temperature, pressure, and variations such as severity of cyclic changes, the life of the tube is affected by the phenomena occurring both on the tube's external surface in contact with the flue gas as well as its internal surface in contact with the process fluid. So in other words, again, if we look at the picture there, you can see that there's coke inside the walls of the tube, and then also on the outer side of the tube wall, there's some scale. So in other words, the charge that actually, or the load that goes through these tubes will affect the tubes, and also then the high temperatures inside the furnace. Okay, so the reference that was used is again Process Technology Equipment and Systems, the fourth edition, chapter 10 on furnaces. So there's just some pointers here. I think that's also important from these notes that you can also go and have a look at.